next example, find the point on the graph of y is equal to root x that is closest to the point 3 over 2, 0. So here on our sketch, in red is root x, and here is the point 3 over 2 or 1.5, 0, and we want to find the point on the function root x that is going to be closest to the point 1.50. So the distance between the point we want to find and 3 over 2, 0, we can call it d, and d is the distance that we want to minimize. The formula for d will be given by the distance formula, which is just Pythagorean Theorem. So using the distance formula with the points 3 over 2, 0 and xy, d is the square root of x minus 3 over 2 all squared plus y minus 0 all squared. So we can write d as a function of x by plugging in y is equal to root x for y. And the domain will be restricted since y is equal to root x. The domain will be from 0 to infinity. So now we have d as a function of one variable. We plugged in y is equal to root x into the distance formula. So here the square root square will cancel out and we just have x at the end. And if we square x minus 3 over 2, we can FOIL it out to get these four terms. So if we add up the like terms with x, under the square root, we have x squared minus 2x plus 9 over 4. So here now it's up to you. If you want, you can use the first derivative test with the parabola in the square root, or we can also notice that d will be minimized when the inside of the square root is minimized. So here I've written little d, or lowercase d, for just the parabola that's inside the square root, x squared minus 2x plus 9 over 4. So the function little d is an upward-facing parabola since the coefficient of the x squared is positive. For an upward-facing parabola, the absolute minimum will be at the vertex, which will be at negative b over 2a. In this case where b is minus 2 and a is 1, then the absolute minimum will be at x is equal to 1. So here in this case, our reasoning doesn't involve any calculus. So here I will also show the first derivative test, and it's up to you how you want to show the absolute minimum is at x is equal to 1. So the derivative for little d is 2x minus 2. When we set that equal to 0 and solve for x, we will get that x is equal to 1. And then we can check the sign of the first derivative to the left and right. So if you plug in a number that is less than 1 into the first derivative, like x is equal to 0, you will get minus 2. Then you see that the first derivative is negative, so the function is decreasing. If you choose an x value that is greater than 1, like x is equal to 2, the first derivative will be positive, since if you plug in 2, the first derivative is positive 2. So the function is increasing on that interval. So since our function is going from decreasing to increasing, at x is equal to 1, we have a local min there. We only have one critical value on our domain. The local min is an absolute min. And as you said before, both little d and big D are minimized at x is equal to 1. So the distance big D is minimized when x is equal to 1. When x is equal to 1, y will be root 1, which is 1. So the closest point is the point 1, 1. The following problem is about optimizing the strength of wooden beams. If you look up in older buildings, you might notice large wooden beams which form the supporting structure of the building. The strength S of a rectangular wooden beam is proportional to its width W, and it's also proportional to the square of its depth D. Find the dimensions of the strongest beam that can be cut from a log of diameter 12 inches. In this sketch, we have a cross-section of a log. The diameter of the log is 12 inches, and the cross-section of the beam that we want to cut out of the log is this rectangle. It has width W and depth D. We want to maximize the strength S of the beam. The strength is proportional to the width, and it's also proportional to the square of the depth, where k will be a constant of proportionality, and k can be different for different types of wood, and we will just treat it as a constant. Next, we'll use Pythagorean Theorem to write d squared in terms of w. So 12 squared is equal to w squared plus d squared. So then we can write d squared as 144 minus w squared. And we can plug that in for d squared. So S of w will be kw times 144 minus w squared, which is constant k times 144w minus w cubed. For the beam, both the width and the depth must be greater than or equal to 0. If we isolate for d from this formula with d squared, d is equal to the square root of 144 minus w squared, and that must be greater than or equal to 0. So w squared must be less than or equal to 144, so w must be less than or equal to 12. So the domain will be from 0 to 12. S prime will be equal to k times the derivative of 144w is 144, and the derivative of minus w cubed is minus 3w squared. So we'll set the derivative equal to 0 and solve for w to find the critical values. So it's up to you. You could divide 0 by a k to get rid of it. Here I multiplied it out. 144k minus 3kw squared is equal to 0. So 3kw squared is equal to 144k. So we'll isolate w squared. We can divide both sides by 3k. And then the k and the k will cancel. 144 over 3 is 48. W squared is equal to 48. And next we can take the square root for w. So we'll consider only the positive w. 48 is 16 times 3. Square root 16 is 4, so w is 4 times root 3, which is around 6.93 inches. Next we use the first derivative test to check the sign of the first derivative to the left and right of the critical value. So if you plug a number that's less than 6.93 into s prime, then you can check that you'll get positive values for s prime, which means that s is increasing on that interval. If you plug in numbers that are larger than 6.93 into s prime, then you can check that you will get negative values for s prime, so s is decreasing on that interval. Just note that k is a positive constant, so it won't affect the sign in your calculation. Since the function is going from increasing to decreasing, around the critical value, we'll have a local max there. The local max is an absolute max. So the strength of the beam is maximized when the width is 4 root 3 inches or 6.93 inches. Next we will plug in w to solve for d. So d is the square root of 144 minus w squared. W is 4 root 3. So check if you get that d is square root of 96, which is the square root of 16 times 6. So d is 4 root 6 inches, or around 9.8 inches. So the dimensions that maximize the strength of the beam are 4 root 3 by 4 root 6 inches. And here are a couple of buildings that were built more recently using new types of engineered wood. These wooden structures can be a sustainable alternative to concrete and steel buildings.